Yeah, so just going to start at this point again, just to go over it. So this is like the whole header now. And of course you can't read any of this, but this top bit, that was the part we saw before. And everything below is going to be perhaps more similar to what you would expect to see in the CPP file. So we go here. This is like what that top red box was. This is what looks familiar, except with the difference of template class T. And the return types and whatnot, it's all T. And who here remembers what T means? It's kind of like a variable for type, yeah. It's basically a stand-in for like, well, whatever type. All the new stuff we're going to end after class node open squiggly, close squiggly, semicolon. So under there, in the header file, this is where we'll see like the default constructor. But we write template class T at the top, and we would write from the class node T colon default constructor. The not default constructor. The only real difference here is that one, it's in the header, and two, we just switched out the T and added the template class T thing. Other than that, it's basically exactly the same. Copy constructor, great. Wait, what's this say? Is this a deep copy? Looking for some sort of answer. No, nobody knows, huh?
I'm gonna say no.
Why are you gonna say no?
50-50 shot.
Because it's a 50-50 shot. Well, I guess that'll remain a mystery. Nothing in the deconstructor because there's no need to delete anything here. We're going to assume that whoever created the data that perhaps the thing of type T is going to be pointing to, whoever created that data, they're the one responsible for destroying that data, for deleting that data once we're done. This is just like the array in the sense that I can delete the array, but then you might ask, well, when you delete the array, do we go through and delete all the contents of the array if those things were dynamically allocated? The answer is no. The array doesn't do that because it's up to you to delete all those individual things first, then delete the array. Same thing with this link structure. Delete all the individual things if you have to, if they're like pointers to things in dynamic memory. Then you can delete the stuff. But here we don't need to delete anything. Getters and setters for the data. Basically the same as before, and getters and setters for next. Basically the same as before, but of course, again, these are in the header file, and we put that template T and use the T for the type instead. And this is what the CPP file will look like. It'll say include no.h, and then that's it. You don't even need that comment. You just have include no.h, and you're good to go. That's all. But when we build this program, it's going to generate the code for us. It's going to make it for whatever type we're using. It's pretty neat. Yeah. Here we're testing it. What is the type? What is going to be the contents? Okay, let me reword this. What is the type of the data for that node there? An integer pointer. How did you know? I mean, there's a lot of ways you could know. Kind of obviously, I guess you could be like, well, what did we set the data to? Well, a new integer, right? Okay, yeah, fine. But really, the easiest way to know is like, well, what was in the little like triangle brackets, the less than and greater than sign? Well, int star, an integer pointer. What's the type of the data in this example? It's just an integer. Not an integer pointer, it's just a regular old integer. Okay. What's this one? It's a node. So the data for this node is going to be a node that contains integers. Why? Because I can. Do you always want to do this? Probably not. I don't know. Maybe you can do it. That's what a lot of computer science is. A lot of times in the class, people ask, like, well, can you do this? And a lot of times, it's like, well, if you're following the rules, you can do it. Doesn't mean you should do it, but you can do it. And a lot of times, when you ask those questions of, like, can I do this? That's where computer science can get kind of weird. But we'll see more of that much later. Anyways, any last questions about the generic nodes? We're going to be looking at generics basically for the rest of the class. So it'll get reinforced, reinforced, reinforced. Any questions? All right. So now, let's learn about stacks. Who here remembers stacks? Of course you do, because we just learned it like a week ago. So stacks. So we're going to use a link structure to make a stack, make the link structure generic, and really we're going to see how to interface what. We're going to see how, like, I know I was emphasizing this before, like, remember, how you use the stack is independent from how the stack actually does what it does. Right? What can I do to a stack? I can push, pop, peek, is empty, size, right? Those are the things I can do with a stack. When I say that, like when I explain to you what pop does, oh, it gets the thing from the top. Does that tell you anything about how that stack was implemented? No. It tells you how you can use it, but it doesn't tell you what's under the hood. Just like if you gave me a car, and it's a standard car, I could probably drive it without knowing exactly what's under the hood, because I know how to interface with the car. So here, push, pop, peek, is empty, size, and toString. Why not? This is what we can do with the stack. We saw this before. What we can do is independent from how it does what it does. This is key. This is very important to understand. This is something that when I was learning it, it wasn't really emphasized very well for me. And then finally, years later, it clicked, and I was like, oh, I wish I understood this more back in first year. But this is a very key idea. The what and the how are separate. So these are just a bunch of operators. Does any of that say, okay, this just says what it can be done with the stack. It says nothing about how the stack is implemented. Nothing at all. Just like last time, I showed you this is what a stack is. Then later we implemented it with an array. That was the how, the array implementation. But the what is the push, pop, peek, is empty, size, toString. It says nothing about where we store the data. It says nothing about how the operators do what they do. It just says what they are. That's it. And perhaps an even more important thing to emphasize is not only does none of this have to do, like the what and the how are separate, but the what and the programming language, like none of these ideas have anything to do with C++. If I tell you the lecture, if I give you the lecture today, and then you go home and you decide you want to implement a stack in Python, great, go ahead. You want to do it in Java? Fantastic, more power to you. C#, great, I don't care. All of this stuff, all that matters is we're talking about what we can do. And we're going to look at a how, another how. We already looked at the array one. We're going to look at another one. But you can take all of these ideas and implement them in any of these other programming languages too. All these ideas are very separate. And this is, the reason I emphasize this is you'll probably remember from weeks ago, I was emphasizing this class is about data structures. This class is also about the algorithms that go with the data structures. This class is not about C++. It's not. I realize we're using C++, but you're kind of, I don't want to say missing the point. That's not really what I mean. It's, you know, not seeing the forest through the trees type thing, where you are, don't focus so much on the C++. Obviously that's important to learn because we're using C++, but the big picture ideas here are the algorithms and the data structures, and all of these things are going to be independent of the programming language. So, this is the definition of the ADT. A collection of data and the operators we use with the collection of data. So, we need to start caring about the implementation details, all right? So, we spent a whole lecture already talking about what a stack is, and we saw the array implementation, right? But based on what this set of slides was titled and what we just learned, can anyone think of any other type of container we might be able to use to create a stack? Like a series of linked nodes or something, right? Does that seem reasonable? Let's build a stack with these linked structures instead. Okay, so that will hold on to the data. And we can keep track of the top of the stack. Well, that's really easy. We could just have like a pointer to like the top of the stack, right? Think of that link structure, right? Yeah. We also need to keep track of how many things are in the stack, on the stack. I don't know what the proper terminology would be there. How many things the stack has. That's probably going to be pretty easy. We could probably just use some sort of integer counter, right? That's basically it. So we'll use a series of nodes, but we're going to use the generic nodes. Because then if we use the generic nodes, we can actually make a generic stack, which is really good. By the way, just to be clear, we could make like the generic array stack as well. It doesn't have to be the node stack to make it generic. It's just by the way. So here's the idea. This is what we'll do. Take a second and look at this. Top is going to be a pointer to like, it kind of looks like the head of that linked structure, right? Remember last, like yesterday? That was yesterday, right? We had class yesterday? Yeah. When we think of those things we did with the stack, how we were inserting things, removing things, based on all those different versions of the insertions and deletions, removing. What, if I wanted to push something on this stack, first of all, look at this, think to yourself, talk to each other, where should it go? If the top of the stack is that like bluish color, where should it go? Well, clearly it should become there. It should go right there, right? Right? And if I remove it, where should I remove from? Well, I mean, this one should go. So based on all those linked structure stuff we looked at last time, which insertions and deletions do you think are going to be particularly relevant here? In the beginning, at the starting, yeah, of course. In fact, are we ever going to have to remove something from the center of that stack, or link structure? Add anything to the middle? Add anything to the end? Remove anything from the end? No. In fact, this stack is actually really easy to implement with this link structure, yeah.
Wouldn't it be easier, though, to have the top be at the end because it's a null pointer, so it'd be much easier to like add something on just by changing the null pointer versus popping it off?
I think it's similarly trivial to add something in the beginning and remove from the beginning. And we would still need a pointer to keep track of the thing that, like if we had the top at the end, if the top's pointing to a null pointer, then how do we get like the previous thing? We can't. We would still need a pointer that gets us to the beginning that we would have to traverse through. Yeah. I like the way you're thinking though. What other implementations can we use? I always think about that. There's nothing saying you couldn't implement it this way. In fact, I should emphasize that. We're at the stage, like this isn't 161 anymore, we're halfway through 162. So you're at the stage where you're good enough programmers that you can start asking these types of questions. Could I implement it this way? Probably. Try it. Is it any good? Maybe. Maybe it's not. In fact, the next set of slides is going to be the computational complexity stuff. Finally, we're going to look at that. I've been talking about it a bunch, but that's computational complexity. That's the stuff where I say like, oh, if there are n things, how long does it take to do a linear search? Like n, right? once we learn a little bit about that, we can start to think, okay, if I implement it this way, what does that mean in terms of computational complexity? Is there a better way to implement that in terms of computational complexity? Stuff like that. Yeah?
In the slide previous, you used the term like generic nodes to make like a stack generic.
Yeah.
What other kinds of like nodes and stacks would there be?
Well, like if I made like
I'm just confused.
the
with
integer pointer stack. Remember the array int stack?
Yeah.
That wasn't generic. Like I hard-coded the fact that it was an integer pointer data in the stack. But we created those, and when we looked at the nodes the first time, I created like an integer pointer node. But then later, what we just did at the very beginning of today was reviewing the generic stuff where we replaced those like int stars with t's, where we can make whatever type. That's the generic stuff. So if we use generic nodes, we can create a generic stack. So it's not restricted to like an integer stack. And then like lab last week, where you had to go and convert all the ints to characters, right? That was kind of a pain. Well, now if we make it generic, we're in great shape. Then of course, we can make the array stacks generic as well.
Okay.
Yeah. So if we pop, yeah, pop again, yeah, there we go. It's fairly straightforward. You might even find this implementation kind of easier. So where's all the action happening? Well, we already answered that. Push pop at the top. Which type of insertions, deletion? All the stuff at the beginning. Okay, top will be pointed to, like, instead of head, we'll have top. Okay, great. And it's going to be a generic node. Count will just be the number of things in the stack. Great. So here's our array integer stack. We had max, top, and int star star stack. And we had our four constructors, our push. Of course, we need expand capacity, right, with the array. Will we need an expand capacity with the linked one? No, because it just kind of inherently will just grow whenever it needs to, right? We just keep adding to the beginning of that list. So we don't need that. That's cool. Pop, right, peak, size is empty, two strings. So we're going to do this, but with the linked stack. So we're going to make it generic. So note the template class T at the top. And we are using the node class as well, the generic one. So, yeah, we have that. Yep, yeah. So, node of type T, pointer, top. It's going to be a pointer to some node. That's going to be the top of the stack. That's it. And we have our count, obviously. We've got our, I guess, 3 constructors here. And push, pop, peak, size is empty, 2 string. And this is the linked stack CPP file. Of course, it's going to be empty. Because where do we actually write all that code now?
Header.
Back in the header, right. So, remember, we're making it generic, so all the code's got to be in the header. So, let's look at a default constructor. Okay, so the default constructor, what should top be pointing to when we create it? Who wants to take a wild guess?
Pointer.
Makes sense, because what's in that stack? Nothing. Great. Also, remember here, back on this example, we had the not default constructor. What did the not default constructor do here versus the other one? Remember the default constructor created the array of a certain size. But we may have wanted an array that was bigger to start in case we knew we were going to have a lot of things or something, right? We don't need to do that with the linked stack, right? Because it's just going to grow arbitrarily by every time we do an insertion, which is pretty cool. So what's the size going to be? Like, what's the count of the stack going to be once we create it? How many things are in it?
0.
Good. That's it. So here's a copy constructor. Well, it's going to be big. You couldn't tell. We'll copy over the count. If the stack we're copying is empty, top is null pointer, right? If I want to make a copy of the other stack, then it's going to be empty. Like if it's empty, then it's going to be pointing to nothing. Empty. If it's not empty, well, we're going to have to create a new node and copy over the top. and then move top to like our top be the current new, right? So we had to make a copy of the node then we create an old, what's this old cur? Have a node pointer for iterating through the old stack. Makes sense. So we've got some old stack here. Calling it old, the one we're copying from. We have a top. Why? People keep like collecting. I think people are doing it for fun. They just bring in bad markers. Right? And what have I done so far? All right, I created a new node called new cur. It's a copy of this node. So I make a copy of this node. Okay. And then I say top is equal to new cur. But of course, this is this top, and this is the other object's top. Okay? Yeah? No?
Where's the difference?
Where's the difference? This is from the stack I'm copying. This is the stack that is being created from a copy of the other one. So that's why we saw obj top. And this here, I could have written this to make it more obvious that there's the difference, but we didn't need it. So this is where we're at currently. And then I have old cur is going to be this. Old cur is going to be a pointer to this one's top. This is where we are. So while old cur's next is not null, so at this stage I know that old cur must not be null, because if it was, we would have triggered that, like if that would only be true if count was 0. So if your next is not null, new cur, oh right, I also have new cur. This was from before. I forgot to draw that pointer. New cur set next to a copy of old cur's next. So old cur's next is this one. Make a copy of it and set new cur's next to that copy. Great. Then what? New cur equals new cur's next. Okay, so that doesn't point there anymore. That points there. Old cur is equal to old cur's next. There. And then we just repeat until we get to null. Any questions about that? All this loop does is iterate through that linked structure. Yeah?
Once you get to the end, like to null, how are you going to tell like the last thing to point to null on your new copy?
On the new copy?
Automatically?
Because what will old cur's next be?
Oh.
Null pointer. So set that one's next to null pointer. Good question though. But it just conveniently worked out for us, I guess. Other questions about it? Yeah?
So that process that you did just now with the with just that one round, are you saying that it just does that over and over again and copies over the old stack as the new stack?
Well, this whole thing is making a copy of the stack.
Okay.
The while loop here is what's going to iterate through the linked structure and ultimately copy over the linked structure that makes up the stack, like the contents of the stack.
Okay. And all of that is just to add something to the top of it.
Say that again?
So all of that is to add a new item to the top of that stack?
No. No, this is the copy constructor. This is just if I wanted to make a copy of a stack object. If I have a stack with 20 things in it, and I'm like, you know what, I want to make a copy of that. This is how to make a copy of that stack. This is not pushing anything on the stack. Not at all. Nothing here is adding anything new. It's just making a copy. Is this a deep copy? Yes? No? Raise your hand if you think yeah. Really high, I want to see. Raise your hand if you think no. I think no. Why do you think no?
It's not taking the same value, the same object. It's creating new ones and just.
Well, that actually kind of makes it a deep copy, based on your explanation. But this is actually not really a deep copy because we don't know, like when we make a copy of the node, do you remember? This all hinges on if you remember what the copy constructor was for the node object. Yeah?
Is it not shallow, not deep, but
it's kind of in between.
it's in, you have two pointers to the same thing. It's not like they're both pointing to the same thing. You have a copy and then you have the original.
Yeah.
But they're both pointing to the same thing.
If you remember the node class's copy constructor said copy over the contents of the data variable, the data attribute, and copy over the contents of the pointer attribute. If the data attribute was just an integer, I'd be copying over the integer, everything would be fine. But what if the data attribute was a pointer to something? Right? Like what if this was a pointer to a human object, and the human object was over here in RAM for some reason? So this was a pointer to there. I copy over the contents of data, I just copy over that memory address. This would then not be the deep, deep, deep copy. I tried to get you.
So deep copy would be making a copy of the person as well?
Yes, but that's the responsibility of the node class if we wanted that to happen, but we don't in this case because if someone really wanted that, it's up to the programmer, but there's arguments for not doing the deep one here. Well, now we need to delete this thing. If we want to deconstruct this object, well, I'm going to create a pointer called toDel. And no, you don't have to call it toDel, that's just what I called it. toDel for toDelete. If the top is not null, set top to next, delete toDel. toDel equals top. Repeat. Yes?
Shouldn't you, by having top equal to top get next right away, does that not delete the original top?
No, because toDel is pointing to top. What?
Can you draw it out?
Yeah, I'll draw it. There's no magic here. You're trying to connect too many dots. You're thinking too hard. Don't skip any steps. You're thinking way too hard.
It's sort of like priming it for the next time through.
Pardon?
Is it sort of like priming it for the next time through? So like toDel is already the top, and then since like the top was top hit next, the next time through it'll be the next one.
Well, let's just draw it. We'll see if that kind of connects. Everything's fine. So let's say I've got some sort of link structure. Top. Can you see this reasonably well at the back? Yeah. Let's say that's the end. So I've got top. What does this code say? All right. toDel equals top. Okay. toDel. TD. I'll just draw it TD because I'm lazy. This is our current situation. Then I say, okay, is top not null? Okay, in this case it's not. So what do I say? Top, go to your next. Okay, great. So do this. So the top pointer just moved. This still exists though, as of now. But then the next line of code I say, okay, delete toDel. Okay. Okay, so that's our current situation. And then I say, okay, toDel, now point to top again. All right, sure. So I think yes was the answer to your question. You're just kind of like setting it up to delete it next time around in the loop. Is that cleared up?
Yes.
Perfect. Fantastic. If this was Python, where we didn't need to worry about the dynamic memory, I wouldn't need to worry about deleting, because Python has a garbage collector that will come along and delete anything that doesn't have a reference to it anymore. So I could have just said top equals top get next. Like if I was in this situation again, if there was a garbage collector and I were to do this, and nothing references this anymore, the garbage collector will come along and be like, nothing references this. That means it's useless. That means I can delete it. Yes?
So we just to like break the chain at the end and then everything gets into shift the top to the last one.
I don't understand the question.
Instead of deleting the one elements, can't we just break the chain at the end and then get rid of the whole thing?
Well, we still have to delete everything that was created. And so this loop gives us the easiest way to delete it. We can't say delete it all. We could write a function delete it all, but eventually in that function there's going to have to be a loop to go through and put our finger on each one to say delete, 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 delete. If this was Java or Python, if I wanted to delete this whole thing, imagine this link structure is a billion things long. And I've got top pointing, this is the head, whatever. And I wanted to delete this whole thing. And my programming language is a garbage collector. And there's a billion things here. All I have to do is say, oh, top, be equal to null. And now nothing references the head, right? So what does that mean? Well, the head can be cut. Oh, now nothing references the next thing, so that's cut. And then that's cut, and that's cut, and then that's cut, and so on, and so on, and so on. It doesn't matter that it references anything. Like a node has an X, great. Doesn't matter if nothing references it. And then it'll like cascade all the way down. Delete, 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 delete. Yes?
Could you feasibly, or is it just theoretically, build like a garbage collector to run in the background of the C++ program?
I suppose so. Don't. Because that's one of the things, right? It's because there is no garbage collector, and you're in charge of it, C++ is going to be faster, right? If you want the garbage collector, don't use C++, because you're kind of like ditching one of the big benefits of C++, I guess. Although I shouldn't say that, because everyone has their favorite programming language, so whatever. Yeah?
If you switch the lines there, delete and top equals top get next, would top get next still be able to get next?
Say that again.
If you switch the delete with top equals top get next, would you still be able to get next, or would it?
No, because if I deleted 2del, top and 2del would be pointing to the same thing. And then if I deleted 2del, that would be like doing this. So I'm in this situation. Then if we said, before moving this, if I said delete 2del, this would happen. Then I would say, top, what's your next? And then C++ is going to be like, that's not what? I don't know. It doesn't exist. Great question, though. I thought I saw another hand somewhere. No? Okay. So this is the deconstructor. Push. Okay, all right, well, what are we going to do? Create a new node with the thing we want to push. Great. I don't know what the type is. I just pass it along, create a node with that data in it. This is just calling the constructor the not default constructor in the node. A node of type T. Then I say new node, set its next to top. Does it matter if top is null at this point or not? What does it mean? Let's say top is null. What's the new node's next going to be? Null. Null pointer, right? Which makes sense because if the top was null, that means there's nothing in the stack. So new node's next is going to be top, and then top is now going to be pointing to the new node. Great. That's it. What does this mean? We'll draw it. Let's say it's null. So here's what I do. I create, new node, n is a new node with the data. Great. When I say new node, set your next to top. Okay, so your next is, I'll just do a dot for null. And then, oh, top, b equal to new node. Okay, great. Great, we're in good shape. Now, if this wasn't a dot, I could replace this with an arbitrarily long link structure, right? Doesn't matter. I still just created a new top and put it in the right spot. I inserted to the front of that link structure. And of course, I have to increase count. Don't forget that. Pop. Well, remember last time, what do we do if we try to pop from an empty stack? Well, we'll throw the exception because why not? Because I don't know what you want to do if you're the programmer using the stack. What do you want to do if you pop from an empty stack? Does that mean something has gone critically wrong and your program needs to stop immediately? Or does that mean you need to ask the user for input again? Or does that mean well, you can carry on, it doesn't really matter so much? I mean, I don't know. So I'll throw the exception, and the programmer using this code later on can decide what they want to do. They'll handle the exception however they want. But otherwise, we'll take the node we want to delete, and it's going to be set to top, because the top is where we're going to be removing from. That's where we pop from. So I've got this node called our del node. Again, the variable name doesn't matter. Get the data from the node I want to delete, of course, because that's the thing I want to return. Remember, when I pop from this stack, it's not the node that I'm returning, it's the contents in that node that I'm returning. In a similar way, it's not the index of the array I'm returning, it's the thing at the index in that array that I was returning with the stack. And then, okay, top, set it to its top is its next, great. Reduce count, delete the node, and at the end of the day, what do I got to do? Return popped. Any questions about this one? Do you want me to draw it again? Yeah? Yeah, all right, I'll draw it. So we're in this situation. Let's say we're here. And if for whatever reason, if your YouTube doesn't work later tonight and you forget how this all worked, just follow the instructions. The code tells you exactly what to do. The algorithm's right there. So what do we have? Okay, it's not empty. We're in this situation. So I create a new node, a new pointer to the node, del node. DN for a delete node. Oh, and it's going to be pointing to the same thing top points to. So there. So far, so good. Now I get the data from the node I want to pop. Okay, so now I've got popped. I don't know, X is in there. Who cares what that is? So I'm going to have popped. So P now has the data. So we're holding on to that because we're going to want to return that. Top, set it to its next. So top, what's your next? Oh, it's this one. All right, top equals top next. So this is now our current situation. Reduce count. Okay, great. Delete this thing. Okay. And then return popped. That's it. Now let me ask you something. Remember before in the copy constructor for the node, I asked, when we made the copy of the stack, I asked, was this a deep copy or not? It was kind of in between, because we didn't go all the way down, because we may or may not have made a copy of the data or something. Because what if the data was actually like a pointer to some object somewhere in RAM? We never made a copy of that. Similarly, when we deleted the stack, or if we delete the node, we're not deleting what that node's data might be pointing to. Because remember, we were saying someone else is responsible for that information, right? That was our rule. Imagine for a second, we don't know what T is here. Imagine X is a pointer to some human object, some student object or something, I don't know. Or if you've read assignment to a cell object, okay? This is critical, pay attention. Imagine my delete for a node. Imagine that my deconstructor for a node, if I did code, oh, go delete the thing that you're pointing to. Imagine that the delete did delete the data, right? Because we could have coded it that way very easily. If I said delete this node, so this is a person object. P, excuse the fact that I didn't plan my real estate very well here. And this points to that, right? Let's pretend that's the scenario. And my delete for this node, oh, did the deleting the data. So imagine I just ran this line of code. I did everything and then I run this line of code. What's going to happen? Well, first I would go delete the data itself. I would go delete that data. Then the node gets deleted. So we're all good. And then I go to return pops. What's wrong? There's nothing there. We just deleted pop. This is a very, very, very good and clear example as to why it would probably be a bad idea to have the deconstructor for the node delete the contents of that data. Similarly with the array, remember, when we delete an array that's been allocated dynamic memory, it does not go through and delete all the, if there's pointers to things dynamically allocated in that array, it's not going to go through and delete all those things. Node's not going to do it either. And look, imagine if we did, we'd be in big trouble. So it's a good thing, because the node is not the one responsible for that data. The node is just holding on to it temporarily. That's it. Someone else is responsible for creating it, they're going to be responsible for deleting it. But of course, in the stack class, the linked stack, we're creating node objects in dynamic memory. So when we delete, when we were writing the deconstructor for the stack, it was the node class that was creating the new nodes. Every time we pushed something, we created a new node that became the new top. So when we delete the stack, we're going to want to delete the nodes, because the stack class was the one responsible for creating those objects. So that's the one, the stack class will want to delete the nodes, because, let's go back to push real quick. See, every time we created a new node there, this is within that stack class, we're going to want to delete it in the deconstructor like we did here. We went through and deleted it all. But not the data, because the stack class is not the one responsible for the contents. It's responsible for managing its own stuff. Peek. Well, this one's going to be kind of easy. Exception if it's empty, otherwise return the top's data. That's it. But leave the top alone, but still return whatever the data was in there. Okay. Size? Well, that's easy. Return the count. Is empty? Is the count 0? What's another option for is it empty, based on how we saw it implemented so far? Here's one way I could write it. Any other obvious way that you can think of right now off the top of your head?
No.
If the top is pointing to null, it's empty. Yeah. ToString. How do we know how to print out a thing of type T? Pardon? Say that again? Auto? Well, we've got a bit of a problem here, actually. Because something of type T, remember how there was the standard libraries ToString, right? The standard libraries ToString was one that took like a number and turned it into a string. And then we wrote our own ToString for our student class. So we could tell a student object to like ToString itself. And then because we knew that we had the course class, we know that the contents of that array, or the container, because I suppose we could have used a link structure, we know that the data is going to be students, and because we know that the data is going to be students, we know that students have a ToString, so I can call the ToString. But now I have something of type T, which may or may not have a toString just there for us. Here's something that really annoys some programmers. So in Python, what function, method, were we guaranteed to get in every object we ever created? What was one of the few methods that we got for free, whether you wrote it or not? Repr is the one I'm looking for. There's other ones too, but repr is the one I'm looking for, because the repr is like Python's toString. So, if you never wrote the repr in Python, Python gave you one for free. And it would just be print out the memory address where this object is in RAM. Not particularly useful, but you got it for free. But because you got it for free, Python was written in such a way where all objects must have a repr, it gets it for free, whether or not it's there or not. C++ doesn't have that. But because Python does, I can guarantee that I can go through this link structure and ask it, give me the string of whatever type T is. I don't care what the type T is, because I know that there must be a toString for it, whether you wrote it or not. It might be useful, it might be their first and last name, or it might be a bunch of garbage memory location. Point is, it must exist. C++? No. So let's do some quick testing. Stack. I created a stack. What's the type of this linked stack? What's the thing? What is the data going to be? On the count of 3, yell it out. Integer. Good. What should its size be once we create it? And is it empty? Of course. After I push these 10 things, should its size be? Is it empty? Of course not. Almost feels kind of silly. Whatever. Here's doing the copy stack. Just a bunch of stuff. Okay. Point is, the one thing I really want to emphasize here is, if I went back, imagine for a second I wrote the generic array stack. Okay? So we have the generic array stack and we have the generic linked stack stuff. And they're all implemented just fine. Okay? They're both there, they're both perfect, they're correct, whatever. Now, here's a really big deal. This is one of the things that I was talking about earlier, one of the concepts that didn't really click for me when I learned it first. I could take, look at all this code, right? So there's this code. If you were to type this into Python or into C++, or copy it into C++ with all the linked stack, the generic linked stack or whatever, all this code will work just fine. I'm going to hit run, and it'll work. It'll work perfectly. It's going to give you the answers it would give you. Now imagine for a second, I decide, you know what, no. I don't want to use the linked stack. I want to use an array stack for whatever reason. All I need to do, there's one line of code I change. That's it. I change one line of code in all the code I just showed you. All I have to do is change link stack int star stack equals new link stack int open close semicolon with array stack int star stack equals new array stack int open close. Everything else will be the same, because the fact that I have a pointer to a stack. Let me put it this way. Imagine this, right? Oh, you can't see. If I do this? Imagine I didn't show you this, but I told you that stack is a pointer to a stack. But you don't know what kind of stack it is. Does that matter? Can you get the size from a stack if it was implemented correctly? Could you ask a stack if it's empty? Could you push things on a stack regardless of if it's a linked stack or an array stack? Does that matter to me right now writing this code? No. It matters to whoever implemented the array or linked one. But at the end of the day, it doesn't matter to me, the person using the stack. I don't care if it was linked or an array. I can push, get its size, check if it's empty. I can peek, I can get the size, I can get empty. I can make a copy of it. Peek size is empty, all that stuff. I can delete it. I can delete the stacks. and it doesn't matter if it was array stack or a linked stack. Because the how is done on the back end. The what, the push, pop, peek, all that, that's the what I can do with it. And that's independent from the how. So, all of this code, it doesn't matter if it's a linked stack or an array stack. The actual functionality of this stack, the actual using of the stack as a stack is the same. All right, we'll end there.